Good afternoon, everyone. I hope everyone's doing well. All we're going to cover today is bypassing ASL, or sorry, not ASLR, that's next week. Bypassing DEP. So I did a video on a basic vanilla buffer overflow, just as I learned some exploit development here. So next, I'm going to pass on to you guys how to bypass DEP. It's fairly simple. It's not that hard, and it's really cool. So here we will go. We will jump into our terminal and we'll get going right away. So what I want to do first is show you guys just something I made up in Draw.io. I am not an artist, so don't judge me on my poor art right now. But this is what we're going to be doing today. So once we jump into our memory, we're going to see a buffer. We're going to see next to the buffer is the base pointer, the EBP. Right to the right of the EBP is the return address. To the right of that is arg1. To the right of that is arg2. And this is how it's laid out in memory. Now, we are going to bypass DEP. We're going to turn DEP on. DEP was turned on our last video. Or turned off, sorry. We're going to turn it on this time. And then the basic exploit is we're going to fill the buffer in the EBP with A's. Within libc library, we can get system exit and binsh directly from that library and call it. That way we're not executing anything on the stack, which DEP prevents. So this will hopefully be clear as mud as soon as we open up our terminal and jump inside. So right away, first things first, let's open up our terminal. I have mine on my desktop. Okay, so the thing is, compile it. So when we compile with DEP, if you want to turn DEP off, you use Z exec stack. We're not going to do that today. We're going to keep our DEP enabled. However, we're going to do no stack protector, and all this does is it keeps us from stack smashing, and we do that at the very beginning here, filling in with A's. There's ways to get around that, and I'm going to get into those over the next couple of weeks. So our program was called Tiny C, little C program, and then output, we're going to output to Tiny. And that's how you compile it. Let's open up. I don't know why I didn't show you this at the beginning, but this is the little program we just compiled, okay, into an executable. Just a simple C program with str copy, which is vulnerable to buffer overflow because it doesn't check bounds, okay? So let's jump into GDB. That's where we live. That's where I live. And boom. Okay, first things first, we're going to disassemble the main function. And first thing I'm noticing is subtraction from ESP 0x20. So most of us start to learn hex after a while, but I know a lot of you don't right off the get-go. So you print /d, which means print in decimal 0x20. You can use your programmer calculator for this if you want, but it's right here in the command line, so why not use it? And 32 bytes. So this instruction here is subtracting 32 bytes from the stack pointer, and that's where the base pointer is going to be. So now we have an idea how big our stack is. I'm going to say display, I want to display 14 words in hex from the ESP. So a word is 4 bytes, as we all know. So I'm going to get 14 of these. So that's going to be my first thing. Next, I'm going to put a breakpoint in here so we can see our inputs as they go in. This is going to be a bit of a process, and we're going to keep going back and inputting things onto the stack. So let's set our breakpoint just below the str copy so we can see what gets put in. And now I'm going to run it, and I'm just going to put in 4, 5, 6, 7, 8. I'm going to put in 8 A's, which should take up 2 of the words in our input buffer, right? So let's run it. And right here, this stuff up here, don't worry too much about this. This is the PETA plugin. if you type in PEDA GitHub, you should be able to find it. It's used for exploit development. We don't really use it in this class. However, it's just there in the background. So just pay attention to the basic GDB buffer area down right here. And as you can see, 4141, 4141, that's our two groups of 4 large A's, okay? So we can look and see, okay, so where is the base pointer? I can make an educated guess where it is right away, of course, but we can just print EBP. Computer's being a bit slow here. Okay, so that's at F108. So we're at F100, 378. This here is our base pointer, which means this right here is our return function. This here is arg1, and this here is arg2. So let's go back to my little diagram I made up in Draw.io again. I'm not an artistic person whatsoever. I did pretty good in coloring in junior school, but that's about it. So right now we have A's filling up only part of our buffer. We want to fill the full buffer full of A's. We also want to fill the EBP full of A's. In the return function, which I showed you right to the right, system, arg1, the exit function, and arg2, the binsh function. So let's have a look. Let's get the buffer filled up and the EBP filled up. So we've used 4, 8 bytes, and that filled that up. So we're going to need 4, 8, 12 more bytes. So let's put in 20 A's. So we're going to run. Now I'm going to jump into some Python because trying to type out 20 A's is pretty weak. so let's do print big A times 20. Let's see what that looks like. And as you can see, 4, 8, 12, 16, 20. We have our EBP written over. This is our first step in bypassing DEP. So now we have to overwrite these 3, our return function, arg1, and arg2. So how I like doing it is go back to our last exploit we wrote, and I'm going to add 4 B's, 4 capital B's. And I'm going to add 4 C's. And I mean, you can use anything for this, but like I just like keeping it simple and organized. You can put in duck or whatever you want, really, as long as you know what it looks like in hex, right? So, okay, so now I just finish this off, put our tick in and close it off. So now let's run this. And as you can see, the A's fill up right our full buffer and our EBP. The B's fill up our exit function or our return function. And then arg1 and arg2 are also filled up with C and D. Okay, so that's our basic fundamental part of our exploit. Next, I'm going to open a new terminal. I like keeping notes in terminal, it's just how I learned. So I'm going to put a hash in here. Next, we need to find the system, the exit function, and the binsh, which are all in the libc library. And that's what we're doing. Instead of executing anything on the stack, we're going to the libc library and grabbing those. And that's how we get around DEP. So first I want the system, because that's what we're doing our return address on. So actually, I'm going to run this again. And I'm going to print. You can do this with read ELF. It'll show you where this stuff is, but then you have to calculate the offset. This here is a simpler way. If you want me to show you the ELF way, hit me up and we can do that. This is so much simpler though. So all we do is just print system. And you can see here in the libc, this is the address in libc for system. So I'm going to copy this. Oh, I messed up here. So we'll just go system equals, and we'll put our system address in here. Wonderful. Next, we're going to look for our exit function, which is going to go over our argument 1. So let's print the exit from libc. And here it is right here. Here's our exit. Wonderful. And as you can see, these are all 4 bytes memory. word. So they will fit into the BBB, CCC, DDD that we made, right? We just put in a dash and or a slash and an X, make it hex, put it in backwards because a little Indian convention, and we're good. So that's our exit. The only one that's either a bit different, we just got to use find. And let's do bin sh. Let's find that. And as you can see, here's bin sh in the libc library. And here we go. So let's put bin sh equals. Wonderful. So we have all our components to get a shell on this and bypass DEP. So the next thing I'm going to do is come back to our last exploit we wrote. So now I'm going to start filling in one of these at a time. So basically I just put some X's in here. And now you're going to read the system address backwards, little Indian convention. So it goes into the stack backwards, right? So we had to put in 10 first. So X 10. Then we come over and we see 33. Let's go 33. Then E5. E5. And then B7. Okay, so that's our system call. Let's run that and see if that lines up good. And I like doing it one at a time because I always leave an X out. I always mess up. So if you do it one at a time, you can sort of have a look and see if anything's messed up. And as you can see, system up here and system right here on the return address look identical. So we're good there. Okay, so let's go back to our exploit. And now let's fill in the C's. So this is covering up our argument 1 with an exit function. And here's our exit function up here, which we've already gotten. So again, it's going in backwards. So 60 and then 62. Oops. And this is where the errors happen, right? You're a human and you're trying to put it in. And yeah, so if I don't mess this up, I'll be surprised. But this is why I like doing it very, very slowly. Okay, so we see our A's have filled up the whole buffer and EBP. We have our return address overwritten with system call. And then, as you can see, there's a problem. There's a problem. And this is why I do it this way. As you can notice, this here doesn't line up with the exit. And I can almost assure you, I forgot an X on the B7 and it comes up as an E. Just watch, because I kind of know hex. And as you can see, note the 60 is backwards right here. Do you see that? That's the error right there. So this is why I like doing this slow and just taking my time and going back through it. Let's put the X over here, just human error, guys. Okay, so let's run this again. And as you can see, boom, the exit function is now agreeing with the exit function we found up here. Everything looks great. So all we got to do is overwrite these D's on the second argument. And we got to overwrite that with bin sh. Fun. So let's haul the D's out of here. So finicky, right? So X, 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 X. Okay, so let's start off here. Now we're putting in our bin sh, so 4C, and then 5D. I almost have these memorized at this point. 5D, F7, and B7. Fun. B7. Whoops, we got a little messed up here. This is what happens. B7. In quotes and our little tick. Okay, that looks good. And as you can see, there is an error. And this is why we do it just like this. So let's come back here again. Yep, there's the error right there. X after the C. This is why we do it all at once. Otherwise, it'll turn into a mess real fucking quick. So let's put an X. Oops, nope. Here we go. Okay, let's run that. And as you can see now, boom, everything looks copacetic. B7, F7, yep, 5D, 4C. We now have our exploit ready. And now when we run this, it should spawn the shell, and then we can get shell while bypassing all DEP protections. So let's run. We hit continue, and you can see new process is executing new program, bin dash. So I have my shell, and that's how you bypass DEP. In the following weeks, I will cover ASLR, stack canaries, all kinds of fun stuff like that. One thing I want to cover just before I go is shell codes. I was asked about last time in my video. I write my own shellcode. I'm going to do some videos on writing your own 32-bit and 64-bit shellcode. It's not that hard, the basic shellcodes. However, for practice, if you want, you can come over here to shellstorm.org and you can get all the different exe, bin.sh shellcodes here to practice with. So if you don't know how to write your own shellcodes, you can check out this website. There's a few other ones out there, but this one seems to be the best. So I'm going to leave it there for today. I hope you guys enjoyed. I will be back next week with another video, and I hope you guys enjoyed. Take care, guys. Bye.